This is universal gravitation. This is Newton's law of universal gravitation. Newton determined this relationship here. What he said was, in the universe, objects put an attractive force. So one object puts an attractive force on another object. And the way that this works, this relationship is G is the gravitational constant, always 6.67 times 10 to the minus 11, 10 to the negative 11. And in here, we would put the masses of the two objects. It says right here point masses. So when the distances involved between the objects are really far, even something like planets going around the sun, the distances involved are so vast that we'll treat the planets as point masses, just a little point. We'll treat the sun as a point, and then we can figure out the distance between them. That's r. So r is not the radius, but it's the distance between the masses. And so you put those numbers in this calculation. And what Newton is saying here is that is what gravity is. It's a gravitational force that's attracting these two objects together. Okay, and we have some units here, newtons, kilograms, meters. I put the units for the gravitational constant, although that's not too important. Sometimes when an object is much more massive than the other, we'll, instead of M1 and M2, we'll use capital M and little m. And let's go ahead and see how we would solve one of these problems. Here we have two masses of 1,000 kilograms each. The distance from their centers, we treat them as point masses. The distance is 1 meter. And the right mass is putting an attractive force on the left mass, which we call the gravitational force Fg. And we're trying to calculate what is that gravitational force. And so over here, I've put in G. I've put in mass 1 and mass 2. They're both 1,000. And the distance between them is 1 meter. So we'll square it. So let's calculate it. And okay, so I've already gotten started here, 6.67, but let's back up a little bit. Um, yeah, you can do times 10 to the, but it's much faster if you use this feature on the calculator. It's some notation here. So you hit second and you hit the comma, but it gives you that EE, which is like exponent. And what it means is 6.67, E means times 10 to the, and so we'll have to write negative 11. Now, notice it's not to the power of negative 11. You're not going like this. You're not doing that. Um, Oftentimes when I see students do that, you get an overflow error, means that the calculator can't handle the huge numbers that you're trying to put in there. So anyway, then we have 1,000, and then we have 1,000, multiply them. And then at the bottom we have 1 squared, which is just 1, which we could have just left out. Cool, and you get this, 6.67 times 10 to the negative 5. Um, you know, if you have it in scientific notation, that's fine. So we'll come back here and we can say 0.0000667 newtons, or 6.67 times 10 to the negative 5 newtons. Yeah, however you want to write that. Whatever the calculator gives you, I think is fine. Now notice the gravitational force between two 1,000 kilogram masses. Now that's a lot of mass. Like, I don't think you can carry that amount of mass, right? That's a lot of mass. Um, but look at how much gravitational force there is between them. Very small. It's not even a Newton. Much, much less than 1 Newton. So gravity is very weak. It takes masses on the order of planets and stars for gravity to really have like a strong effect. In fact, if we calculate here, the net force on this mass just due to gravity, that's Fg, We can calculate what the acceleration is of this. How fast, or what rate will this object accelerate towards the other one? This would just be Fg over m to give you acceleration. This is 0.0000667 over 1,000. And so it becomes even smaller. Um, I believe this is 6, let's say, oh, we could add 3 more zeros. 1, 2, 3 meters per second squared. So the acceleration is incredibly small. Okay, let's keep going. And so here we have big M, little m. Big M is 2,000 kilograms. Little m is 1,000 kilograms. They're separated by 1 meter. Which force of gravitation is greater? Which one is pulling the other one with greater force? And if we were to calculate the purple one, well, that's G, M, M, the two masses involved, separated, by a distance r, so over r squared. If we were to calculate the blue one, it's G, the two masses involved, and the distance between them squared. And so, of course, when you plug in those numbers, of course, it's the same equation. This equation tells you the gravitational force pulling both of them together, this one and this one. It's the same amount. Or I should say this one, or both. And so we go back here, and of course, this Fg that we calculated, it's also on this mass over here. And of course, that goes back to Newton's third law. When one object puts a force on another object, second object simultaneously puts a force on the first object, but in the opposite direction. Now, just moving along. Here's the Earth. Here is you with a 1 kilogram object, little m. You're holding it 1 meter above the ground. And we want to know, what is the gravitational force on your 1 kilogram object? Let's use big M, little m over r squared. What did we use before? Yeah, we use m1, m2. Cool. So what is the gravitational force on that object? This is 6.67 times 10 to the minus 11. Use parentheses. Make a fraction here. Big M is the Earth, 5.97 times 10 to the 24. Little m is your 1 kilogram object. And the distance between them, that is from the center of the Earth to where you're holding that 1 meter above the ground, it is essentially the radius of the Earth. It is essentially this distance. You can trust me that if you add 1 meter to 6.37 times 10 to the 6 meters, that's this many meters. Yeah, 6,370,000. If you add 1 to this, you can take my word for it that that doesn't really change the distance very much. In fact, you won't really see that. For several decimal places, you wouldn't see that effect. One thing people forget is the squared on the bottom. So 5.97, trying to memorize everything, but let's just type this in. What was it, 97? See, I've already forgotten. 0.9724. And then we'll put 1. And the distance between them always moves my spot here. 6.37 E6. and that's squared. Oh, I still have this in scientific notation. Let's get rid of that. Just get a number 9.81, which is not surprising. Shouldn't be surprising anyway. Newtons. This is why it's not surprising. We've done this back when we did forces. The gravitational, well, actually, anytime we do draw a free body diagram, the gravitational force on an object is mg. And so the mass of your 1 kilogram object, now normally we use 10, but if you want to use the real number, it's 9.81. And so the gravitational force is 9.81 newtons. A much faster way, this is using Newton's law of gravitation. But that's what we're learning here, so it's important to know how to do this. Cool. So, on a planet, let's say you have, or let's do it like this, sorry. The gravitational force on some object, let's use big M, little m over r squared. So let's say you're on the surface of the planet, and so your distance is capital R. The gravitational force is G times capital M, the mass of your planet, and little m, the mass of some object on the surface of that planet. I don't know if I said Earth, but any planet really. Fg is equal to gmm over r squared. And we know from what we've been using, little mg, we can substitute little mg here for the gravitational force and bring this over. And look at this, the little m cancels. And so this relationship tells us that the gravitational field, G, on any planet is G mass of the planet over r squared. Notice that the mass of any object on the surface of that planet that's in that gravitational field doesn't show up anywhere in this equation. And r, capital R, is the radius of the planet. So this is the gravitational field equation, basically at the surface of the planet of mass capital M, radius capital R. Oh, and yeah, I forgot to mention this in class. The units for G are newtons per kilogram. Newtons per kilogram. So that would be the units of that right there. Oops, a little g. Oops. Anyway, let's keep going. Okay. Let's see, do I still have time? Yes, I do. So here we have the sun, the earth, and the moon in this position. And by the way, oh, I'm making this video. We're about to have a total lunar eclipse. And so this is essentially what happens is the moon finds itself in the shadow of the earth. You know, the sun's over here. And the moon turns red. Maybe not that red, but anyway, there you go. So question here is, the first question is, how many forces are there total? How many gravitational forces are there? And so I think I'll use green. I'll start with the moon. The moon is getting pulled with an attractive force from the Earth. So I will call that F of Earth on moon, FEM. The moon is also getting pulled this direction. Oh, I should do this a different size because it's probably a stronger force, but I'm not exactly sure if it's stronger. But this is F that the sun puts on the moon, FSM. Okay? The Earth is getting pulled back to the left by the moon. So I'll call that FEM, Earth. So the moon, it's the same magnitude, just opposite direction. The Earth is getting pulled towards the sun. So I'll say sun on Earth, FSE. The sun also gets pulled this way from the Earth. Let's call that F, what do I use, SE? They are equal in magnitude. And then there is a force that the sun puts on the moon, or vice versa, the moon puts on the sun, FSN, going that way. So there's six forces, gravitational forces total. But really what I'm seeing here is three calculations. Because FEM, FSM, and FSE are those three calculations. Here are the masses, and the distances between them are shown up here, and the masses are here. What is the net force on the moon? In other words, what is, and I use different notation when I wrote this, what is the force that the Earth puts on the moon, gravitational force, and what is the gravitational force the sun puts on the moon? We need to add those together. So F net is FEM plus FSM. So let's see. You know what? I think I want to do this separately. My subscripts are not that good. These are really supposed to be real tiny subscripts here. So the fourth force that the Earth puts on the moon, just do this calculation really quickly here. We need the mass of the Earth, 5.97 times 10^24, and we need the mass of the moon. This is wrong. Oh, no, no, this is right. Yeah, 7.35 times 10^22. Now, what's the distance between the Earth and the moon? 3.84 times 10^8. Squared. So here we go. 6.67 E minus 11 times 5.7 E 24 times 7, I've already forgotten, 7.35 E 22, divided by their distance apart, 3.84 times 10^8. Hey, looks good to me. Syntax error. This happens sometimes. Yeah, I see it right here. 5.97. There we go. 1.98 E20. The E20 is important. That's your order of magnitude. Cool. Let's calculate the sun gravitational force on the moon, 6.67 times 10 to the minus 11. The sun is 1.99 times 10 to the 30, I believe. And the moon is 7.35 times 10 to the 22, divided by their distance. Now, should I model this good, well for you? The distance between the sun and the earth is it's a huge amount greater than the distance between the earth and the moon. This is clearly not drawn to scale. Look at the orders of magnitude here. So I think I've added these before, and it barely even changes that. We could add them. I'm not going to. This is 1.5 times 10 to the 11. Oh, I've got a minute. I'll show you that. 1.5 times 10 to the 11. 3.8. Let's add those and look what you get. Well, so now I have the number. I'll use the real number, 1.5038 squared. Wish I could keep these side to side. I'm gonna figure out how to do that right now. So what do we have? The sun, and then we have the moon, 7.35 E22. Ah, here I am trying to corners here. 35 E11, and of course I needed to square this. So hopefully I haven't gone too fast. 4.31 E20. Newtons. And we can just add these two numbers together. Net force is 1.98 times 10 to the 20 plus 4.31 times 10 to the 20. Now you'll see that those don't really change. We can just add 1.98, 4.31. Take that plus this 6.2. All right, let's call it 6.3 E20. Whoops. That's the net force. And if you're showing your work, I kind of rushed through this to get this done because the bell's gonna ring here, so I had to hurry. You know, make sure you're showing all of your work here. You're showing your equation, like so. And I think that is it for gravitation.